Assalamu alaikum dear students. I welcome you to 31st lecture of probability and stochastic processes. In previous lecture, we finished our discussion of random vectors where we observe more than one quantities and we put them in an order manner, and then we assume that this ordered collection of observations is coming from an ordered collection of random variables. So a random vector is an ordered collection of many random variables. We talked about joint PDF, joint CDF of random vectors and a few applications of random vectors. We talked about transformation of a random vector to another random vector, or transformation of a random vector to a scalar valued random variable, and we worked with in greater detail a particular transformation where z was a transformed scalar valued random variable which was equal to sum of a finite number of random variables. So z was defined as x1 plus x2 plus x3 plus all the way to x capital N. So z, a scalar valued random variable, was sum of a finite number of random variables. This was an important case, and we tried to find the PDF of this transformed random variable from the PDF of the individual random variables used in that summation. And we also assume that for a simpler case, if all the random variables being used in the summation are identically distributed and independent of each other, then it's very easy to find the PDF of transformed random variable z, and one approach we discussed was based on convolution integral. If we have a transformed random variable defined as sum of two independent random variables, then the PDF of transformed random variable is equal to the convolution of two PDFs of random variables being used in definition of z is equal to x1 plus x2. And this argument can be extended to n random variables where z is defined as x1 plus x2 plus x3 all the way to xn, and in that case PDF of z is n-fold convolution of all PDFs of random variables used in the summation of z, in the definition of z where z is obtained as summation of a finite number of random variables. We also talked about characteristic functions, which are expected values of a special complex valued transformation from a real valued random variable. We learned that if we take characteristic function of a convolution integral, then the answer is multiplication of two characteristic functions, where first characteristic function is the characteristic function of first PDF used in the convolution, and the second characteristic function is characteristic function of the second PDF used in the convolution. So if there are two independent random variables, you add them together to define a transformed random variable z, then the characteristic function of z is equal to multiplication of characteristic functions of the two random variables that are added in the definition of z. When we extended this argument, we saw that if we add a few independent random variables, the resulting transformed random variable looks like a Gaussian random variable. We proved that if the random variables being added are Gaussian themselves and independent of each other, then the PDF of the transformed random variable is definitely the PDF of a Gaussian random variable. So sum of a finite number of independent Gaussian random variables is also a Gaussian random variable. But when we added a few independent uniformly distributed random variables, their characteristic function approached a characteristic function which looked like characteristic function of a Gaussian random variable. So if you keep on adding more and more independent random variables to define a transformed random variable z, then the result approaches closer and closer to a Gaussian random variable. So this process of moving from fewer to more and more and more random variables in the definition of z and approaching closer and more closer to the PDF of a Gaussian random variable is usually analyzed through the idea of convergence. In today's lecture, we are going to have a detailed look of convergence, particularly as it applies to random variables. So let's start with simple case of convergence of numbers. So if we have a collection of numbers indexed, so there is a first number, second number, third number, and we have an infinite collection, countably infinite collection of numbers, and they approach a certain destination. So when they approach a certain destination, then they behave in a certain way, and if they do so, we say that a sequence of number converges to a destination or final value. So if the collection of numbers is x1, x2, x3, x4, xn and beyond, and the destination value is x0, then we say that the sequence of numbers x1, x2, etc. converge to the destination value x0. If as they move on, as we go on in index values, we go closer and closer to the destination value, and if we pick a certain limit, then we will not be going away from the destination value more than that limit. We will see a precise mathematical definition of convergence in a while, but let's have a look at a few sequence of numbers and see if they appear to be going towards the destination or not. Our first sequence of number is xn is equal to n. The value is the value of index. So the sequence is 1, 2, 3, 4, 5. The sequence does not appear to be approaching a destination. It just keeps increasing and increasing and increasing. The next sequence is xn is equal to 1 over n. So actual values are 1, 1 over 2, 1 over 3, 1 over 4, and so on, all the way towards infinity. This sequence appears to be approaching the value 0, because as the denominator of this simple fraction keeps on increasing, the value of this positive fraction keeps on decreasing. And this is always a positive number for positive n, but its value will be decreasing and decreasing, so it will become smaller and smaller, and it will approach a destination value of 0. For any finite number n, the actual value will be 1 over n, slightly more than 0, but eventually it will become closer and closer to the destination value of 0. Here, this sequence is defined recursively. xn is equal to square of previous number xn minus 1. So if you define this in this recursive manner, you have to give a starting value. If x1, the starting value is larger than 1, then x2 will be square of this number which is larger than 1, which will be larger than this number, because the starting value is larger than 1, the subsequent values will be even larger. So this sequence with this starting condition and this recursive definition is not converging to a destination value. The values keep on increasing and the sequence goes towards infinity. But the same sequence recursively defined with a starting value smaller than 1 will converge to a value 0, because if starting value is less than 1, the subsequent values will be positive but smaller than the previous value. So the next value will be even smaller, and this sequence with a starting value less than 1 will converge towards 0. The next sequence is xn is equal to square root of the previous value. So if the starting value is a positive number, if it is larger than 1, then the subsequent value will be smaller than the previous value. So this sequence will converge to 1. And if the starting value lies between 0 and 1, then the subsequent values will be larger. In that case also, this sequence will converge towards a destination value of 1. The last sequence is xn is equal to cosine of previous number. If these numbers are expressed in radians, I want you to use your calculator or any scientific computing software like MATLAB and try to see the values of this sequence. If you find a few values, you will see that this sequence also converges to a value. I want you to do that to see what that value is. Let's have a look at the precise mathematical definition of convergence. So if you have a sequence of numbers xn and this approaches a destination value x0, then it is called to be converging to this value if you pick a number delta. This is called the limit. Pick any small number delta greater than 0. Then after you pick this, I'll give you a capital N. So you pick the limit, I'll give you a value n in such a way such that whenever the index n of this sequence is greater than this my provided value n, then the absolute value of difference between numbers after n and the destination remains less than your limit. So you can pick even smaller limit and I will decide a capital N, and once I decide that, all the numbers xn with index n larger than this value will remain within your limit. Here is an example. This is a sequence of numbers xn is equal to 1 over n. So this is 1 for index 1, this is 1 over 2, 1 over 3, 1 over 4, and they go on, and this sequence appears to be converging to 0. So you pick your limit delta. Suppose you pick this limit, which is approximately 0.3. So if you pick 0.3, I will pick an index 4, and after this index 4, or even for this index 4, the values of this sequence will always be so that they will not be away from the destination value of 0 more than your limit of 0.3. You can pick even a smaller limit, say 0.05. Then I'll pick a capital N, which will be 21 or so. And after the index 21, the values will be smaller than 0.05, or it will be closer to the destination value by a distance of 0.05. So this is how you define convergence mathematically in a precise manner. You first pick a limit, and then you have to find an index, and after that index the sequence remains very close to the destination value, closer than the limit that you started with. You saw in this example of xn is equal to 1 over n that once the value of this sequence falls within the limit that you selected, it remains within the limit. The sequence keeps on going smaller and smaller and smaller. Let's have another interesting example. This example is shown here, where the values of the sequence are shown as the lengths of these vertical lines. And this sequence is from the equation xn is equal to e raised to power minus n over 25 multiplied by cos of n over 4. So this sequence goes starts from positive, goes negative, then positive, negative, positive, negative, is oscillating because of the presence of this cosine factor. And the amplitude is becoming smaller and smaller because of this exponential factor. So is this sequence converging? Let's see. Let's pick a limit. So we'll pick a limit of 0.1. If we pick a limit of 0.1, then we have to make sure that we pick an index so that after that index, the sequence remains within 0.1 of its final destination value. So we will have two lines here at plus 0.1 and minus 0.1. Since the numbers go positive as well as negative, we'll have this strip of width 0.2 centered on this horizontal axis. And let's have a look at the sequence of numbers. It starts with a big value. Here it is within that limit, but then it goes out of the limit again. Here it is within the limit but goes out. Within the limit, goes out. 4 or 5 values within a limit again go out. But after this index, even when the sequence becomes larger than the previous value, it remains within this bound. So you cannot pick this as your index, you have to pick this one. So after this index, the sequence still behaves in an oscillating manner, but the amplitudes of those oscillations are decreasing, and after this index, the sequence remains within 0.1 of the final destination value of 0. So this sequence is a converging sequence, and it converges to a final destination value of 0 in an oscillating manner. There are other tests to see if a sequence of numbers converges or not, and you can consult a textbook to see what those tests are, like Cauchy's test and other tests. Let's talk about convergence of functions. Convergence of numbers is easy to understand. You have a sequence of numbers and they converge to a destination value, which is also a number. When you talk about convergence of functions, then you have a large collection of indexed functions. There is first function, second function, third function, and there is a destination function, and we say that this sequence of functions of certain parameter defined over a certain domain converge to that destination function if, as you move from first function to second function to third function, you go closer and closer and closer to the destination function. It's easy to define closeness of two numbers because distance between two numbers is easy to define. It's absolute value of the difference of the values of the two numbers. But how do you define the closeness of functions? You define it indirectly as closeness of numbers, the values of the function for a particular value of the parameter. If the function is from real numbers to real numbers, and you can assume that the real numbers of the domain are represented by x and the results are y, so function is y is equal to first function of x, second function of x, third function of x. So y1 will be first function of x. But you take a particular value of x, say xs. Then this is the number that you look at. y1 is equal to first function of xs, y2 second function of xs, y3 third function of xs, and so on. Then you look at these sequence of numbers, and if these sequence of numbers converge, then the value of the function goes closer and closer and closer to the final value, which will be y0 equal to f0 of xs, where f0 is the destination function. So a sequence of functions f1, f2, f3, f4, all the way towards infinity is said to be converging towards a destination function f0, if for every point in the domain of these functions, the sequence of numbers f1 of xs, f2 of xs, f3 of xs converges to f0 of xs. Let's have a look at a few sequences of functions and see if they appear to be converging towards a final destination function or not. Our first function is x raised to power n. So this is the sequence of functions. First function will be x raised to power 1. Second function will be x square. Third function will be x cube, x4, and so on. So if they are defined over an interval from -1 to 1, where the endpoints -1 and 1 are not included in this interval, then you will see that you pick a number from this domain and the value of these sequence of functions will be the power of that number. So suppose you pick 0.5. So the first function value at 0.5 will be 0.5, then 0.5 square, then 0.5 cube, and so on and so forth. So if you have limited your interval from -1 to 1, all these sequence of numbers will be going towards 0. We just saw in the previous slide that this is the case. If you take a number smaller than 1 and raise its powers, then the number goes down towards 0. So all the numbers in this domain will become smaller and smaller, and the destination function will be a 0 over this interval. So a 0 valued function over this interval is the destination function, and this sequence of functions defined over this domain is a convergent sequence of functions. Let's take the same sequence of functions x raised to power n, but change the domain from -1 to 1 to -10 to 10. With this extended domain, the sequence of functions does not remain convergent, because if you pick a number larger than 1 in this domain, say 5, then the value of first function at 5 will be 5. The value of second function will be 5 square. The third function will be 5 cube, and so on. So the sequence of numbers for domain value equal to 5 will not be convergent. Hence, this sequence of functions for this extended domain of -10 to 10 is not convergent. The next example of functions is sine of n times x. I have not specified a domain, you can take any domain. And this function is not convergent because if you look at the sequence of functions, it is sine of x, sine of 2x, sine of 3x, 4x, 5x, and so on. So this sequence of functions takes the first function and plots it as a sine wave. The second function is also a sine wave with double the frequency of the first function. The third is also a sine wave with a frequency 3 times the first one. So this is a collection of sine waves with higher and higher and higher frequencies, and all those go from 0 to 1 to -1 to 0 again, and they keep on oscillating with maximum peak to peak amplitude of 2. So you can take any value in domain other than 0, and this sequence of functions will give you an oscillating values from 1 to -1. For 0, all these functions give a value of 0, but a domain larger than just 0.0 will have values which oscillate, and this function is not a convergent sequence of functions. The next sequence of functions is also a family of sinusoids. This is shown as cosine of omega x plus 1 over n. Omega is a constant number, which is the angular frequency. X is the number we pick on the domain, and this is what changes function from value of n1 to value of n2 to value of n3. So the first function in this sequence is cos of 1 plus omega x. The second function is cos of half plus omega x. Third function is 1 over 3 plus omega x, cos of 1 over 3 plus omega x. So as you keep on moving from lower indexed functions to higher indexed functions, this additional quantity in addition to omega x becomes smaller and smaller and smaller. So when this 1 over n becomes smaller and smaller, it converges to 0. Eventually, this will become insignificant, and this sequence of functions will converge to a destination function of cos of omega x. The next sequence of functions is e raised to power minus absolute value of n times x, and this is defined for the whole real line. So if you think about the shape of this sequence of functions, it is like this. From the vertical axis where it is 1, on both sides it decays. For n is equal to 0, it remains 1 for all values of x. For n is equal to 1, it decays slowly. For n is equal to 2, it decays even more. For higher values n, it decays even very steeply, and then it remains closer to 0. So you can imagine as n increases towards infinity, the value of the function at origin for x is equal to 0 remains 1. But for all other values, it goes towards 0. So eventually this will converge to a function which is 0 for all values of real numbers except 0. What about the value of function at 0? When you take n going towards infinity, very large number, and you multiply it with x, if x is non-zero, then this number becomes larger and larger, and e raised to power minus of that very large number and becoming larger and larger is 0. But for x is equal to 0, if you multiply 0 x value with n and n approaches infinity, then this number is undefined. 0 times infinity is undefined. So the value of destination function at origin is not defined, because you cannot define e raised to power minus 0 times infinity. So this function converges to a function which is 0 valued on all points of real line except the origin. The last sequence of function is very similar to the one we just discussed. It is given by e raised to power minus nx for positive values of x, and it is 1 otherwise. So this sequence of function does not change for negative values of domain, it only changes for positive values of domain, and it changes similarly to the behavior of the previous collection of functions. So a sequence of functions can be convergent or non-convergent, and it can converge point-wise on some of the points on the domain and may not converge on a few selected points in the domain. Now let's have a look at plots of a few functions in a sequence of functions. This sequence is given by fn x is equal to e raised to power minus x minus 1 over n inside the parenthesis. So the first function in this collection f1x will be e raised to power minus x minus 1. The second function will be e raised to power minus x minus half. Third will be e raised to power minus x minus 1 over 3 whole in parenthesis. And here is a plot of these functions. The top line shown in red color is for the first function. The green or yellowish green second line is for second function. The blue line is for the third function, and the black line is the destination function f naught of x, which is e raised to power minus x. Why is it so? because if you look at this equation, as n increases, this quantity 1 over n becomes smaller and eventually becomes insignificant. So the final destination function for all the points in this domain will be e raised to power minus x. This ux next to the equation tells that you will take only the positive points of the domain x. So x will only be positive values, and this equation gives this sequence of red, green, blue functions which converge to black function. Here you can see on this graph that at domain value of 0.5, the first function gives a value which is high between 1.5 and 2. The second function gives a value between 1 and 1.5. Third function gives a lower value, and if you keep on going from lower indexed functions to higher indexed functions, the values at domain value of 0.5 will become smaller and smaller and smaller, and eventually they will converge to this value which is e raised to power minus 0.5. This second area also shows that if you take a domain value of 1, the value of first function will be this value which is 1. The other values will be smaller, and this sequence of numbers obtained by evaluating all these functions at x is equal to 1 will give you a sequence of numbers which converge to this value. And similarly, this third collection of numbers obtained by evaluating all these functions at x is equal to 1.5 will also give you a sequence of numbers which start at this value and converge to this black value. So this collection of functions converges to a destination function of e raised to power minus x for all points of domain, which includes 0 and positive values of x. Please note one thing, that all the functions in this collection, including the destination function, are continuous functions. When you move from 0 towards positive infinity and take values of x, you see that function continuously goes in a connected manner. There is no discontinuity. The function is continuous. The neighboring points of the function are very close, so it goes in a smooth, continuous curve. The next collection of functions will show that it is possible to have a sequence of functions which are continuous, but the destination function is not continuous. Let's have a look at that collection. Here, the sequence of functions is defined by this equation e raised to power minus nx if x is greater than 0 and 1 otherwise. So this collection of functions will not change for this part of the domain, which includes 0 and negative values of x. For this part of domain, it will always remain at 1. For positive values of domain, the sequence of functions will start with this red line, which is e raised to power minus x. The next function shown in green is e raised to power minus 2x, so it will decay even quicker. And the third function shown in blue, e raised to power minus 3x, will decay with higher speed. The next line is for n is equal to 5, and this line closer to the vertical axis is for n is equal to 50. So you can see as n is increasing, the functions are decaying in a very quick manner, and eventually this function will decay so quickly that for all positive values greater than 0, it will be 0 valued. You can see that for any small value of domain greater than 0, when n approaches infinity, minus nx approaches minus infinity, and value of e raised to power minus infinity is 0. So for all positive values of domain, the destination function will be a 0 valued function. But what about this value 0? We said that for values which are negative including 0, the sequence of function remains at 1. So we can say the destination function also remains 1. So destination function is 1 from minus numbers to 0, including 0, and then it suddenly jumps to 0 valued function for all values which are greater than 0. So in this case, a sequence of continuous functions which start at value of 1 for negative values of domain including 0, and then they decay quickly. All the functions for finite value of index n have a value which is 1 till 0 and then quickly decaying, going to the x-axis quickly and then remaining very close to x-axis. But the destination function is a discontinuous step type function. Now that we have talked about convergence of sequence of numbers and convergence of sequence of functions, we can move towards discussion of convergence of random variables. You know, random variables are functions. They are functions from the sample space to real line. So they are also functions. So their domain is the sample space instead of real line, and the range is real line, just like the functions we discussed. So we can talk about convergence of random variables. So suppose you have a collection of random variables defined for the same underlying sample space with many outcomes, finite or possibly infinite outcomes. For this collection of random variables, we can index them x1, x2, x3, where x1 is first random variable in our collection, x2 is second, and so on. And we can also have a destination random variable x0. Then we can talk about convergence of this sequence of random variables to a random variable x0 in different convergence criteria. The first convergence criterion that we are going to use is similar to the criterion used for convergence of functions over the whole domain, where we evaluated functions for different values of domain. In case of random variables, domain is sample space. So from sample space, we'll take outcomes. So outcomes are elements of sample space, just like real numbers, values of x were the elements of domain. So we'll take a certain outcome and we will evaluate, we'll find what is the value of different random variables for that certain outcome. So an outcome is when a random experiment is performed and something comes out of it. And then you define a random variable from that outcome to a point on real line. In this collection, you have an outcome, experiment was performed, something was observed, and from that outcome, from that observation, you define multiple random variables taking multiple values on real line. First random variable x1 takes on a value which is x1 of that outcome. The second random variable takes a value on real line x2 of that outcome, and so on and so forth. Now, you will look at all these real numbers or real lines which are generated from this collection of random variables after an experiment is performed and an outcome is observed. So if those numbers, the sequence of those numbers converges to a value, then that value is the value of random variable x0, which is generated for that same particular outcome. So the outcomes take on the role of points in domain for the case of functions. So if we have a collection of random variables x1, x2, x3 all the way to infinity, and there is a destination random variable x naught, and for all outcomes in the sample space, the values of random variables for that outcome converge to the value of random variable x naught for that same outcome, then all these random variables converge to x naught in a manner which is called sure convergence. So sure convergence is very strong. For every outcome you get a sequence of numbers, and that sequence of numbers converges to a number which is the value of the destination random variable. Please note one thing. This collection of random variables, if they are converging in sure convergence criterion, then they cannot be independent of each other. Suppose you have an outcome and you look at the value of 10th random variable and it is quite close to the destination value. What about the value of 11th random variable? Will it be far away from the destination value? No, it will also be close to the destination value. If 10 and 11 do not meet this criterion, look at 700th and 701st. They will be close to each other. So if a random variable with index n takes on a value, then the random variable with index n plus 1 cannot take a value independent of that value. It will take value close to that. So if a collection of random variables converge in sure convergence mode, then the collection is not independent. The random variables in that collection are not independent of each other, they are dependent on each other. Now suppose that you have this sample space consisting of infinitely many outcomes, and a sequence of random variables x1, x2, x3 going towards infinity converges for almost all outcomes of the sample space except a few. They can be a few hundred, a few thousand, or a few 4, 5, 6. But interesting thing is that if you put together all those outcomes of sample space for which the sequence of random variables gives a sequence of numbers that do not converge, and call that collection of outcomes an event A. So event A contains all the outcomes for which the sequence of numbers generated by the sequence of random variables do not converge, and probability of that event A is 0, then this convergence is called almost sure convergence or almost everywhere convergence. If a collection of random variables is converging to a destination random variable x naught in almost sure convergence, then this collection once again cannot have elements which are independent of each other, because for those outcomes for which the sequence of numbers generated by this collection of random variables do converge, for those outcomes the random variables cannot take on values independent of the random variables close to them in terms of the index values. Hence, for sure convergence and almost sure convergence, the collection of random variables cannot be independent of each other. Sure convergence and almost sure convergence are two types of strong convergence. There are other types which are called weaker convergences, and in this type there are three types of convergences where there is a sequence of random variables and they converge to a destination random variable, and the sequence of random variables go closer and closer to the destination random variable, but in a different sense, not in the sense of values of random variables for a particular outcome. In weaker convergences, we do not consider the outcome. Sometimes we just consider the probability of events, sometimes we just consider the CDF or PDF of all the random variables in that collection. The next type of convergence of random variables is called convergence in probability. We have a collection of random variables x1, x2, x3, and there is a destination random variable x0. Then we define events where for a certain value delta, the difference between the value of random variable xn and the value of random variable x0, that difference, the absolute value of that difference is greater than that selected delta. The probability of that event goes smaller and smaller and smaller and approaches 0. So this is the sequence of numbers that we consider. The absolute value of first random variable and x0. Second number is the absolute value of second random variable and x0. So you take this sequence of numbers, and if this sequence of numbers converges in the sense of convergence of numbers that we considered a few minutes ago, then this sequence of random variables x1, x2, x3 is called being convergent in probability. This is slightly weaker type of convergence, and you can look up the details of this type of convergence in your textbook. The fourth type of convergence of random variables is called convergence in the sense of mean square, where you look at the expected value of a new random variable, which is xn minus x0 absolute value. So you have a sequence of random variables x1, x2, x3, x4, and then you have a destination random variable x0. So you define a sequence of random variables which are x1 minus x0 absolute value, x2 minus x0 absolute value, x3 minus x0 absolute value. You don't look at the probabilities but expected values of this collection of new transformed random variables xn minus x0 absolute value. So if the expected value of this sequence of random variables converges to 0, then we say that the sequence of random variables x1, x2, x3 converges to x0 in the sense of mean square, in the sense of minimizing the expected value of square of the difference of the random variables in the collection and the destination random variable. The last type of convergence of random variables is convergence in the distribution. You have a collection of random variables x1, x2, x3 and so on, and there is a destination random variable x0, and then you say that the CDF of x1, x2, x3, x4 becomes similar and similar and similar to the CDF of x0, the destination random variable. In this particular case, this collection of random variables can be independent of each other. Only requirement is that if you have a collection of x1, x2, x3 going towards infinity, then the CDF of this collection of random variables becomes closer and closer and closer to the CDF of destination random variable x0. Nothing is said about the mutual dependence or independence of random variables in this collection, and they can very well be independent of each other but have their CDFs which converge towards a CDF which is called the destination CDF or CDF of destination random variable x0. In today's lecture, we talked about convergence. We covered the fundamental concepts of convergence of sequence of numbers and convergence of sequence of functions. After building that solid background, we started talking about convergence of random variables. There are strong types of convergences and there are weaker type of convergences of random variables. In next lecture, we'll continue to talk about convergence of random variables, and we'll use Markov inequality and Chebyshev inequality to formally analyze the behavior of different sequences of random variables which converge to a destination random variable under different criteria. Till then, I wish you the best. Thank you. Khuda Hafiz.